Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering at Institute of Aeronautical Engineering. So in today's class, we are going to discuss some numerical problems on the dot conversion of the magnetically coupled circuits. In the previous class, we have discussed about the how we can apply this dot convention in the magnetically coupled circuit. So based on this dot convention, so how we can identify the direction of the currents in the two coupled circuits, and as well as based on that, so how we can write the KVL and how we can apply the KVL and KCL at various nodes that we have already discussed in the previous classes. So in today's class, based on those concepts, we are going to solve some numerical problems. So these are very important. Then first, let us go with the problem 1. So here, let me read the problem first. So for the coupled circuit shown in the figure below, determine the values of the currents I1 and I2. So here the currents I1 and I2 that we need to find. So here I1 is the current flowing through the primary winding, and the I2 is the current flowing through the secondary winding, right? So we need to find the primary and secondary winding currents. Of course, here it is very easy that to find the I1 and I2, just simple this is a simple circuits. Okay, so by applying some KCL or KVL or some basic the circuit concepts, we can find I1 and I2. But here the key role, here the dot convention will play the key role, because based on this dot convention, we are going to write the equation which is related to the circuit 1 and the equation which is related to the circuit 2. So by solving these two equations, then we can find I1 and I2. But we should know, okay, because as we have seen in the previous class, okay, in the dot convention, based on this dot, because you can see here for this particular circuit here, this is one dot and this is another dot that they have mentioned. But as you can see, not only just this dot, okay, so here what is the direction of the current in these two circuits is also very important, because as you can see here at this particular dot with respect to the circuit 1, the current is entering, okay, from the dotted terminal. And but in the second case, when you see the second circuit or the secondary circuit, so the current is leaving from this particular dotted terminal. So which means here in one circuit the current is entering at the dotted terminal, and in another circuit the current is leaving from the dotted circuit. So which means here the mutual induction sign will be the negative, because both are in the opposite way. That's what we have discussed in the previous class. So based on this particular concept, now we are going to write the equations with respect to each circuit, and the primary circuit and the secondary circuit, and by solving those two equations, then we can find I1 and I2. So here the major key point is to identify or to apply this dot convention principle to a particular or to a given circuit, right? So first here, let me consider the circuit 1. So in the circuit or the primary circuit, so as you can see here, you just apply the KVL to the primary circuit, okay, or let us find here, because as we know already, here in this case, let us consider here it is V1. So we already know how to find or how to write the voltage across the primary winding. So V1, which is equal to, first of all, what is that? The voltage across this terminal or the primary terminal due to the current flowing through this particular terminal is I1. So which means due to the self-inductance. So here due to the self-inductance, here it is, what is that? Because I1, so let us consider here L into I1, right? L into I1, and minus here it is M into I2. Because here some flux will link with this primary coil due to the current flowing through the secondary coil, right? So that is what this one. And similarly, we can write the equation for V2 also, okay, which is the voltage across the secondary terminal or the EMF, okay, across the secondary terminal. So here V2 is equal to the same way L into, because here L is the self inductance and here M is the mutual inductance, right? So in this case also, let me write L into, of course, the current flowing through, I mean, due to the mutual inductance. So how the mutual inductance will produce because of the same current, okay. So which is I2 minus, because why here we kept minus, because here at the dotted terminal, the current is entering in the primary circuit, and at the dotted terminal, the current is leaving from the secondary circuit. So that's why here the mutual inductance will get the negative sign. So here it is minus M into, and again due to the mutual induction also, some voltage will develop across these two terminals. So that's why, which is M into I1. Right? These are the two equations. So just apply or try to write this, the voltage V1 equation in with respect to the primary side. So here it is V1. Okay, already they have given V1, which is equal to 250 at an angle of 0 degrees, which is equal to whatever the total the impedance, okay, across this particular circuit. So here which is 10 plus J50 into I1 minus, here the mutual induction that they have given, the value of the mutual inductance also, which is J10, okay, into I2. Let us consider this is equation number 1. Then similarly, let me write the equation for the second case also. Okay, of course, let us consider here it is 0, because we don't know the value of the V2 anyway. So let us consider here it is 0. So then 0 is equal to the same way L. Here what is L here? Which is 10 plus 50, because two resistors are there. One is 10 and 50. Another one is J50 into here it is I2 minus, again M is J10 into I1, right? So this is equation number, let us consider equation number 2. So here just simplify, try to simplify this equation number 2. So if you simplify this equation number 2, then we can find the value of I1 in terms of I2. So here it is J10 into I1, which is equal to 60 plus J50 into I2. So which means here I1 which is equal to, so here this 60 plus J50 into I2 by J10. Then if you simplify furthermore, then here I1 is equal to, here 60 by J10 plus, of course here J gets cancelled, then 50 by 10, which is equal, into I2, right? So if you furthermore simplify this, then you will get here, which is, here it is 5, okay. So 5 minus, if you, multiply and divided with J, then you will get here minus, okay. So here then J6 into I2, so which is equal to I1, right? So let us consider this is equation number, before we have considered 2, so this is equation number 3, right? So now if you substitute this I1 value in equation number 1, okay, then you can able to find the value of I2. So wherever I1 is there, you just substitute the value of I1 that we have calculated just now, which is 5 minus J6 into I2. So then substitute these 3 in 1. Substitute the equation 3 in 1, or I1 in the equation number 1. So the equation number 1 here it is 250 at an angle of 0, which is equal to, here 10 plus J50, so 10 plus J50 into here I1, so I1 here it is 5 minus J6 into I2 minus, here again here it is J10 I2, so minus J into J10 I2. So you just simplify this, then you just multiply these two, then you will get here 50 minus what is that, J60 plus J250 plus 300 minus J10, because I'm taking I2 as also common into I2 as a common. So if you further simplify, then here this is real term and this is also real term, and this one is imaginary and this one is imaginary and this one is imaginary, right? So you just add the real terms together and also the imaginary terms together. Then finally you will get here it is 350 plus J180 into I2. So this is what is that, 250 at an angle of 0 is also there, right? So then when coming to the I2, here 350 plus J180, so here I2 is equal to 350 plus J180 into I2 by 250 at an angle of 0 degrees, right? No, sorry, here it is the reverse way, okay? Because here we are going to send this one to the left hand side, so then I2 is equal to 250 at an angle of 0. So I2 is equal to 250 at an angle of 0 degrees by what is that, here 350 plus J180. Now this is I2. So if you further simplify this, then you will get, of course, the same way like in the previous case. Okay, then here the value of I2 is equal to, here I have already calculated, so let me check. Here it is 0.635 at an angle of minus 27.22 degrees amperes. So this is the value of I2. So now we know the value of I2, and now we need to find the I1 value. So from equation number 3, I1 is equal to 5 minus J6 into I2. So here I1 is equal to, so 5 minus J6 into, here I2, the value of I2 is 0.635 at an angle of minus 27.22 degrees. So if you just simplify this or you just multiply this two terms, then you will get here the value of I1. Let me see, here it is 4.959 at an angle of minus 77.41 degrees. So this is the value of I1. So in the given problem, they ask us to find the current flowing through the primary winding and the current flowing through the secondary winding, which means I1 and I2. So now we have calculated the values of I1 and I2, right? So here nothing is, what is that, new concept. Okay, so here the only thing is we just need to identify the sign for the mutual inductance based on this dot convention principle, right? So because in the previous session when we were discussing about the dot convention, right? So here suppose if the direction I2, okay, instead of this way, suppose if the direction is like this, let us consider direction is like this, then in this case here this equation where, yeah, this equation here you will get plus and here also you will get the plus. Because why? Because there you will get the plus. Why? Because here, as you can see here, this dot conversion, and I mean let me write here. Okay, so instead of this, let us consider here this is the direction of the current I2. So in this case, as you can see, in the primary winding the current is entering through the dotted terminal, and in the secondary winding also the current is entering through the dotted terminal, right? Which means the sign for the inductance and the mutual inductance is same. Okay, which means the direction of the what is that, the flux, okay, I mean the direction of the self flux and the mutual flux are in the same direction, right? So that's why then here the equation, let me write here the equation, V1 is equal to L into I1 plus M into I2. Okay, and similarly V2 is equal to L into I2 plus M into I1. So here we are getting the positive sign. So that is what we should understand, because in the previous cases, I mean, only we have discussed if the two dots are at the same location, then you will get the positive, and if it is suppose one dot here and another dot here, then you will get the negative. Okay, but here it is not like that. Not only just the dot, the dots. Okay, so you have to just analyze, okay, whether the current in the two, in the two circuits, whether the current is entering to the same terminal or not. Okay, so that is based on that. Here the sign of the mutual inductance will be depends, right? Next, coming to the second problem, right? So in this, let me read first the problem. So this is the second problem. The circuit diagram of an air-cooled transformer winding is shown in below figure, and the coefficient of coupling between the primary and the secondary winding is 0.70. So here you just see, here they have given the coefficient of coupling instead of the mutual inductance. Here they have provided the value of the coefficient of coupling. Then the coefficient of coupling, here we know the coefficient of coupling is nothing but K, we usually represent. Okay, and we know the what is the equation for that particular, in terms of M and as well as in terms of, M in terms of K. Okay, so here K is 0.77, and the relation between K and M is, as we know already, M is equal to K into square root of L1, L2. So here L1 is the self-inductance of the coil 1, and the L2 is the self-inductance of the coil 2, or the primary winding and the secondary winding, right? Then determine for the circuit, first one is what is the mutual inductance M, and second one is the primary current I1, and the third one is the secondary terminal potential difference. So which means here the first case that we need to find A is what is the mutual inductance between these two circuits, because now we know the coefficient of coupling, then we can easily find the mutual inductance. And the second one, here it is the primary current I1. Okay, and the third one that we need to find, here it is the secondary terminal potential difference, which means V2. So these are the three parameters that we need to find. So first let us go with the A bit, which is the mutual inductance. So here directly we know the equation for the mutual inductance in terms of the coefficient of coupling. So we know what is L1. L1, here it is they have given 1 millihenry, and L2 also that they have provided, L2 is equal to 6 millihenries. So, and we know the value of K also, K is equal to 0.77. We need to just substitute all these particular values in this equation, then we can find the value of the M, which is the mutual inductance. Then here the mutual inductance M is equal to, so here K is 0.77. Okay, and square root of, so here 1 millihenry, which is nothing but here it is 1 into 10 to the power of minus 3 into, and again 6 into 10 to the power of minus 3. If you simplify this, then you will get the value of the mutual inductance. So here the value of the mutual inductance, here it is, after simplifying this, then you will get here 1.715 millihenries. So this is the value of the mutual inductance. So the first one done. Then the second one is I1. So of course, to find the I1, which is the current flowing through the primary winding, again we have to follow the same procedure like we have followed in the previous problem, right? So first we need to write the voltage equation with respect to the primary circuit, and the second, again we need to write the voltage equation with respect to the secondary winding, right? Okay, first let me write here. As you can see, one more parameter that they have given here, it is 20 kilohertz. Okay, which is F, which means usually what it mean actually, here it is XL. Okay, XL is equal to 2 pi F into L, right? So that's what here they have given the frequency. So wherever because in the previous cases directly they have given in the frequency domain, so that directly we have taken L, but here we have to take the XL value, okay, instead of the direct L. So that's why XL is equal to 2 pi into FL. So which means here F is equal to 20 kilohertz that they have given the value, right? Yeah, fine. Then first let me write the first mesh equation. So here let me write the voltage 40 at an angle of 0 degrees, which is equal to, so what are the other parameters? So here it is, one is let me write other way, okay, this way, right? So R1 plus J omega L1 into I1 minus, of course, yeah, here again the concept, the dot convention concept will come into the picture. So whether here we have to write plus or minus. That we need to identify based on this dot convention. Of course, as you can see here, this is one dot and this is another dot, right? As you can see here, this current is leaving from this particular dot, okay, or the same way if you consider, because here it is the coil actually. So here also the same as like the previous problem. So in this case, the current is entering to this coil through this dotted terminal. But here, as you can see, the current is leaving from the coil through this dotted terminal. So here one dotted terminal, the current is entering, another dotted terminal, the current is leaving. So which means both are in opposite way, right? So that's why here the mutual inductance will get the negative sign. So that's why here you are having minus M into, so here what is R? Okay, because here also it is in R in frequency domain. So we usually write J omega M into L2. Okay, sorry, I2. Because the sum of the voltage will produce because of the mutual inductance, and how the mutual inductance will happen because of the change in current flowing through the secondary terminal, right? Okay, this is I2. Then the similar way for the second terminal, the second circuit. So this is circuit 1 and then the circuit 2. Then for the second circuit, of course, anyway, initially we usually considering as a 0. So 0 into, so here R2, L2 and ZL, right? So R2 plus, of course, anyway, J omega, what is that? L2, J omega L2 plus ZL into the current flowing through the particular circuit is I2, and minus J omega M into I1. So let us consider this is equation number 1 and this is equation number 2, right? So now first we need to find the terms here. What is R1 plus J omega L1? So here first let me find R1 plus J omega L1. So here R1 is 5 ohms plus of course instead of omega is equal to 2 pi f. Okay, so that we can substitute. So J into 2 into pi into, so here f is that they have given 20 kilohertz, which means 20 into 10 to the power of 3 into what is that, omega j L1. So here L1 is equal to 1 into 10 to the power of minus 3, right? Yeah, fine. Yeah, this is the R1 plus j omega L1. So if you simplify this, then here of course this one gets cancelled. Then you will get here R1 plus j omega W1, which is equal to 5 plus J 125.66 66 ohms, right? Then similarly, let me find R2 plus J omega L2 plus ZL, right? So here the value of R2 is 40 plus here J into, same, omega is equal to 2 pi f. So sorry, yeah, omega is equal to 2 into pi into, again f is equal to 20 into 10 to the power of 3 into L2, here it is 6 into 10 to the power of minus 3, plus again ZL is 200 at an angle of minus 60 degrees. Then if you simplify this, then you will get here, let me see here, yeah, so 140 plus J 580.77 ohms. So this is this value. Then substitute this particular value and this particular value in equation 1 and 2. Okay. Then let me substitute this value in equation 1. Then equation 1 will become, so 40 at an angle of 0 degrees, which is equal to, so 5 plus J 125.66 into I1 minus of course here let us substitute the J omega M I2 value also. So here let me write here, so J omega M, which is equal to J into omega, again 2 pi into 20 into 10 to the power of 3 into the M value we have calculated already, 1.715, yeah, into 1.715 into 10 to the power of minus 3. right? So if we simplify, then you will get here the j omega m value. Let me see here. What is the value of j omega m? Yeah, j omega m here it is. Yeah, j 215.51 ohms. So you just substitute this value also here. So it will become j 215.51 into I2. So let me consider this is equation number 3. Then similarly, if you substitute this value in this equation number 2, then this equation number 2 will become 0 is equal to what is this value here? Yeah, 140 plus j 580.77 into here where it is, yeah, here I into I2 minus again the j omega m value, here it is j 215.51 into I1. This is equation number 4. Then now we are going to simplify the equation number 3 and 4, or we are going to solve the equation number 3 and 4. Okay. So by solving this equation number 3 and 4, we can find the value of I1 and I2. So there are so many methods are there. Okay, we can follow any one of the method. Okay, either we can just convert into the matrix form, and again by using the Cramer's rule also we can find the I1 and I2 value, or simply by using calculator we can find the value of I1 and I2 values. Here by solving this what is the two equations, then first of all let me write here the I1 value. I1 which is equal to the value of I1 here it is 0.725 at an angle of 65.09 degrees amperes. So this is the value of I1. So actually let me see what they are. Yeah, for the primary current. So the primary current we have calculated. Of course, if you substitute again in this any one of the equation either 3 or 4, then you will get the value of I2 also. But here it is not necessary. They didn't ask us to find the value of I2. So I1 is enough. So that's why we are just done with the I1. Then the third one is now they ask us to find the V2. Okay. So what is the voltage across the secondary terminal? Okay. So the voltage across the secondary terminal, which means this one. Okay. So which means the voltage across the load, which is nothing but the voltage across the load. But to find the voltage across the load, again we require the value of I2. So anyway we have to find I2, because here the potential difference across the secondary winding, which is equal to which is I2 into Z2, because here the current flowing through this particular winding is I2. So anyway we need to find the value of I2. So then again, as I told you before, just let me write the value of I2 also. So here the I2 here it is 0.262 at an angle of 78.64 degrees. So then substitute here, then here let me write here the secondary terminal, potential difference, which is equal to I2 into Z2. So now we know the value of I2 0.262 at an angle of 78.64 degrees into here Z2, that the value is 200. What is the value? 200. Yeah, at an angle of minus 60 degrees. You just multiply these two terms, then you will get the finally the potential difference. Here it is. Let me see. Yeah, 52.4 at an angle of 18.64 degrees volts. So this is the potential difference between the potential across the secondary terminal. So this is how we can find the various parameters by using this dot convention. So here the major key role of the dot convention, here it is just to identify the sign which is associated with the mutual inductance, right? Yeah. So in the next class we will solve some more problems. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.